In our last explainer, we discussed GhostBit. Today we're diving even deeper, right into the heart of digital simulations to uncover the hidden mathematics that can literally make or break a virtual world. Let's jump in.
You know, we've all been there, right? You're playing a game, everything's going great, and then, bam, a crate just launches itself into orbit, or your character starts shaking like they've had way too much coffee. It feels completely random, chaotic. But what if I told you it's not random at all?
I love this image. It's like the crime scene. Over on the left, you've got this perfect, smooth ideal of pure mathematics. But on the right, that's the jagged, chaotic reality of what's actually happening inside your computer. All those little glitches, those vertex misalignments, those are the clues we're about to follow.
So here's the big secret right up front. The chaos you see in a physics engine is almost never random. It's actually a totally predictable, repeatable symptom of a fundamental clash. A clash between how math works in theory and how computers have to work in the real world.
And this really illustrates that clash perfectly. On the left, you have the pure mathematical idea of a sphere. It's infinitely smooth. But on the right, you have hardware's reality, a jagged approximation built from a limited set of triangles. The computer is literally forced to fake a perfect curve using a bunch of straight lines.
And I think this visual is so interesting because it shows you exactly what's going on. Math is that smooth, perfect curve, but hardware is the staircase trying its best to follow along. Every single one of those little gaps between the ideal curve and the hardware step, that's called a quantization error. Every pop, every jitter, every physics explosion. It's basically the sound of the friction between these two worlds.
Okay, so let's meet the first culprit in our investigation, and this is a big one. It's the fact that in the digital world, precision is not created equal. It actually gets worse, a lot worse, the farther you get from the center of your world.
Now, to get this, we need to talk about the ULP, or unit in the last place. Just think of it as the smallest possible step the computer can take at any given moment. It's the literal gap between one number and the very next number the hardware can even represent.
But here's the crazy part. That gap isn't a fixed size. This is what we call a variable grid. Near the origin, the numbers are packed incredibly tight, giving you amazing precision. But as you travel farther out to these huge coordinates, that ULP gap gets bigger and bigger and bigger. The precision literally gets cut in half at every power of 2.
And here's the direct result of that. At the center of the world, your character can move with sub-millimeter accuracy. It feels buttery smooth. But way out at the edge of the map, where that ULP gap might be, say, 10 centimeters wide, your character can't move smoothly anymore. They're forced to just snap from one grid point to the next. That is spatial jitter, and it's a huge cause of those physics explosions.
All right, let's move on to our second culprit. And this one is even more counterintuitive. We're about to enter a world where the basic rules of math just seem to break down. A place where adding two numbers together can result in, well, nothing at all.
Just look at this. 1 million plus a tiny fraction equals 1 million. How is that even possible? Something is clearly getting lost in translation here. And this isn't a bug, it's a fundamental limitation of floating point math called the law of absorption.
So here's the trick. To add these two numbers, the hardware has to line up their decimal points, right? But because the big number is so much larger, lining them up forces the smaller number's important digits to get shifted completely out of the available space. They literally fall off the end into what engineers grimly call the bit bucket, gone forever. The addition happens, but the result is just the original big number.
And the consequence for physics can be absolutely catastrophic. Imagine a planet in a space simulation. Its position is a massive number. But the little nudge from gravity each frame, that's a tiny, tiny update. When you try to add that tiny force to the massive position, the force just gets absorbed. It's too small for the hardware to even notice. The planet just stops moving. It's frozen in space.
So, we've seen how precision can fail us in space, causing jitter and absorption. But there's another hidden trap, and this one isn't really about accuracy at all. It's about a sudden, massive, and often completely hidden hit to your performance. This trap involves something called subnormal numbers. These are ridiculously tiny values, smaller than the smallest normal number a computer can usually handle. And they were actually designed for a good reason, to let values fade gracefully all the way to 0 instead of just snapping there abruptly. It's a feature called gradual underflow.
But, and this is a huge but, that mathematical grace comes at a staggering price.
A standard math operation might take, 1 to 4 clock cycles on a processor? A calculation involving one of these subnormal numbers? That can take over 100 cycles. It's a massive, performance-killing slowdown.
And this analogy just explains it perfectly. Standard math takes the fast hardware path. It's like a direct silicon superhighway. But subnormal math, it gets kicked off onto this slow, whining microcode path, which is basically the CPU having to stop what it's doing and run a little piece of internal software just to handle this one special case. In a game, when lots of objects slow to a stop, their velocities become subnormal and your frame rate can suddenly tank for no obvious reason.
So we've got these three huge problems: spatial jitter, absorption, and this subnormal performance trap. The solution, it turns out, isn't some perfect mathematical formula, but actually a really brilliant piece of engineering compromise.
The fix is called flush to zero, or FTZ. Modern game engines just flip a special switch in the CPU. And what this switch does, as you can see, is it acts like a gatekeeper. Whenever the CPU is about to create a subnormal number, this flag just intercepts it, changes the result to a hard zero, and keeps everything moving along on that fast hardware path. And this right here is the crucial trade-off. By flushing these tiny numbers to zero, we are sacrificing a microscopic, and I mean totally meaningless amount of precision for things that a player would never, ever see anyway. And what do we get in return? We get immense frame rate stability, which, as we all know, is way more important for the actual experience.
So let's do a quick recap. We've looked at three core problems: the spatial ULP, which causes that jitter at far distances; spatial absorption, where big numbers just swallow up the small ones; and temporal subnormals, which trigger those insane performance drops. And we've seen the elegant solution: the FTZ/Deas hardware flags that trade a tiny bit of precision for a whole lot of speed and stability.
And that really brings us to the ultimate takeaway here. A physics engine doesn't exist in some perfect mathematical vacuum. It exists on a grid of silicon, and mastering the quirks and the limitations of that hardware, learning to control the chaos, is the only way developers can create the seamless, stable, virtual worlds that we all love to get lost in.
So the next time you see a physics object go crazy in a game, you'll know. It's probably not random at all, but just a predictable result of the hardware doing its best. In our next explainer, we'll explore the arithmetic anomalies. Stay tuned.